when surface hoar is on the surface. I love it. It's fast and makes a swishing sound. But after a layer of surface hoar has been buried, it scares me. Look at the wild propagation that released this avalanche. In this video, Simon, Horton and I are going to look at some of the science behind surface hoar layers and the insidious avalanches that too often kill experienced riders. Let's start with a case study. In early March of 2000, 4 backcountry skiers skied down this slope in the North Columbia Mountains. They ranged from novice to very experienced. The danger rating for the area was considerable at all elevations. The bulletin for the area noted that surface hoar, 60 to 80 centimeters below the surface, was a serious instability. The slope faces south, and the 4 skiers may not have been expecting buried surface hoar on this slope. They regrouped in these trees and decided to ski one at a time to the trees below. The first person skied down to the trees, then the second followed. While the third skier was skiing down, the fourth person moved a few steps and triggered a 160-meter wide slab avalanche. The fourth skier dropped onto the bed surface. The third skier was carried down slope. He was not injured and dug himself out. All 4 skiers regrouped above the crown, where the 2 more experienced people observed a profile which looked like this. The avalanche released on a layer of small surface hoar crystals on a melt-freeze crust. A pre-trip plan like this one probably would have flagged the avalanche slope as too risky. However, in 2000, these skiers, and many others, did not use a structured trip plan prior to backcountry travel. There are many questions arising from this avalanche that released on a layer of surface hoar. Here are 3 of them. How does surface hoar form on sunny slopes? What factors contributed to the propagation that surprised these skiers? During trip planning, what information would have helped the 4 skiers avoid slopes like this one? These questions and others will be answered in these chapters. However, the necessary information sources and guidance for recreationists and practitioners to manage slabs overlying persistent weak layers like surface hoar is covered in courses and elsewhere. In contrast, this video is for those who are interested in more avalanche science than necessary. Before we get to where surface hoar layers may be triggerable, Simon is going to explain some science behind how and where surface hoar forms.
In the next few minutes, we'll talk about the weather conditions that favor surface hoar formation and how that impacts the terrain where we find buried layers. Surface hoar layers are unique in that crystals form on the snow surface, whereas most other types of snow originally form in clouds. The process of surface hoar formation involves water vapor directly transitioning from the gas to solid phase. The weather requirements to form surface hoar boil down to 2 critical factors. The first is the snow surface must cool below the frost point temperature. The second is there must be water vapor supply from humid air near the surface. The surface temperature is regulated by a complex combination of shortwave and longwave radiation, as well as water changing phase between solid, liquid, and gas. Shortwave radiation comes from the sun and reaches the snow both directly and diffusely through clouds. Most of it is reflected by the snow. Longwave radiation is emitted by objects such as clouds, trees, and the snow surface. The net balance of incoming and outgoing radiation determines the temperature of the snow surface. Under cloudy skies, the net radiation tends to be balanced, resulting in only modest temperature changes. Under clear skies, the net radiation fluctuates much more. The surface tends to warm up during the daytime when absorbing direct shortwave radiation, and then cools overnight when emitting longwave. Here's an example of temperatures measured over a week at Mount Fidelity. Over this period, the air temperature fluctuated between -9 and -4. The snow surface was measured with the infrared thermometer and fluctuated between -19 and -3. During cloudy periods at the start and end of the week, the snow was a similar temperature to the air, as it was absorbing long-wave radiation from the clouds. During the clear sky periods in the middle of the week, the surface temperatures fluctuated more dramatically. Overnight, the surface was emitting long-wave radiation and was up to 10 degrees colder than the air. During the daytime, enough shortwave radiation was absorbed to offset the emitted long wave and cause the surface to be slightly warmer than the air. Surface cooling was a major driver of surface ore growth over this period. After the first partially clear night, 6 mm crystals were observed. After a fully clear night, they grew to 14 mm, and then 24 mm after another clear night, at which point they were buried. Surface ore forms a wide variety of shapes, including plates, wedges, cups, and needles. These shapes depend on the evolution of temperature and humidity at the surface, following the same principles that form different types of snowflakes and clouds. For example, a study by Brad Stanton at Montana State University grew different shapes of surface ore in a controlled cold lab. Here are photos and CT scans of broad crystals grown at a surface temperature of -15 and narrow crystals grown at -30. Broad shapes, like wedges and feathers, most often form when the snow surface temperature is between -10 and -20, while narrow shapes, like needles and columns, form when the surface is colder. Since the snow is much colder than the air on clear nights, large wedge-shaped crystals tend to form when air temperatures are only moderately cold, such as -5 to -10. The other critical factor to grow surface ore is moisture supply. It plays a large role in the rate of crystal growth. Ideal conditions are mild air temperatures, because warm air holds more moisture than cold air. High relative humidity. The fastest growth rates are observed when the humidity of air above the snow is greater than 70%. Under these conditions, the humidity at the snow surface itself is near 100%. And light wind is the most effective at continually delivering moisture from the air to the surface. Up to this point, we've focused on conditions that favor growth. However, crystals are often modified before burial. Certain conditions can cause the ice to either sublimate back to vapor or melt into water. This is common during periods of low humidity, surface warming, or strong wind. This video shows frost on a recycling bin that is gradually sublimating on the sunny side to the point where it's fully destroyed. Wind also increases sublimation, and strong wind can break or knock over crystals. Smaller bits of crystals laying flat tend to form stronger bonds than large intact crystals. Since crystal growth and shrinkage are highly sensitive to weather, complex mountainous terrain causes tremendous spatial variability. Favorable conditions to form surface ore can exist at several scales, including regional, drainage, and slope or feature. At the regional scale, synoptic weather systems cause general patterns in cloud cover, temperature, and humidity. It can be helpful to track when different regions experience clear nights to get an idea of where surface ore may exist. Here's an example of weather conditions across Glacier National Park in January 2014. Over this period, there was less cloud cover on the west side of the park, and air temperatures were milder. Based on numeric simulations, there were much better conditions to form surface ore on the west side of the park. The clearer skies promoted surface cooling, and the milder air provided a better moisture supply. At the drainage scale, aspect plays a large role in surface ore formation. Shaded slopes experience more surface cooling, which favors growth, and sunny slopes experience daytime warming, which can result in shrinking crystals. Here's a hypothetical example where surface ore grows on both sunny and shaded aspects overnight, but then shrinks on the sunny aspects during the day. Depending on what time of day this layer is buried, you may find surface ore on all aspects, or perhaps just shaded aspects.
So, to answer question 1 from the case study, surface ore tends to form similarly on sunny and shady slopes, but the crystals tend to shrink in the daytime on sunny slopes. So, after the next snowfall, buried surface ore tends to be patchy and insidious on south-facing slopes.
There are interesting exceptions to this pattern. Sometimes, melt-freeze crust form underneath surface ore. This likely happens when there's strong shortwave radiation that causes subsurface melting, but the surface remains either cold or humid enough to prevent melting or sublimation of the surface ore. This example is from a prominent layer observed at Mount Fidelity. On the south aspect, there were 8 to 12 millimeter crystals on a 2 centimeter thick melt-freeze crust. On nearby flat and north-facing slopes, there were similar-sized crystals, but without a crust. There are often pronounced patterns at different elevations. During clear periods, it tends to be colder, drier, and windier above treeline. This often favors the growth of near-surface facets in alpine terrain. This thermal image shows colder surfaces in the alpine. At lower elevations, warmer air and shelter from the wind tend to provide better conditions for growth. The ideal conditions for surface soar growth tend to occur in distinct elevation bands. A special case is valley clouds, which form narrow bands of large surface soar. Valley clouds often form after several days of high pressure, where temperature inversions form low elevation clouds overnight, especially in valleys with open water. The tops of these clouds provide ideal conditions for growth, as the clear sky above the cloud promotes cooling, and the cloud itself provides a moisture supply. The resulting band of surface soar can be visible along mountainsides and is often referred to as a bathtub ring. At the slope and feature scales, sky view plays an important role. Looking up from a point on the snow surface, the more clear sky that is visible, the faster the crystals tend to grow. This is why it's common to find larger surface soar in the middle of forested clearings. Slope incline can have a subtle impact on distribution. First, steep slopes often have less sky view because they face adjacent terrain. As a result, steep slopes may cool less than nearby low-angle slopes. This can favor growth on flatter slopes because they're more open to the sky. Slope angle is especially important on sunny slopes because the surface energy balance changes more dramatically with angle. Steeper slopes facing the sun are more likely to experience melting, sublimation, and potentially form a melt-freeze crust. Creeks and open water can cause slope scale patterns as well. It's common to find large surface soar localized around creeks because of the extra moisture supply. This can be particularly dangerous around steep banks and gullies.
Some key points about surface soar formation are that it's driven by surface cooling and moisture supply, but can be modified by warming, sun, and wind. At the drainage scale, these factors often combine to form distinct patterns with elevation and aspect, while sky view is an important factor at the slope scale. The weather conditions that form surface soar can also form surface facets and crests, which can create problems on most aspects and elevations. However, surface soar often forms and persists in the types of terrain where other problems do not, often catching people by surprise.